Hi, good afternoon to all. I will just share the screen. The slide is visible, right?
Yes, sir.
Yeah. Right. Okay. So rest of this course, we are now going to focus on viscous flows. As you know, so far the various methods, the various formulations, the various solution approaches that we were following were all based on the concept of inviscid flows, where viscosity was disregarded. We have seen the applications of each of them, and we have seen where they can give reasonably good results. But then, as we know, reality has viscosity as a fluid property, and we need to move or to capture the physics properly in several applications. We need to consider viscosity, and that's the theoretical approaches to incorporate fluid viscosity to the calculation is what is going to be the focus of what we are going to discuss from here onwards. Now, as we have seen already, there are a few parameters which are not significant, which are not affected by viscosity. And those are the ones that I have listed there: shock angle, pressure distribution, wave drag. In various instances, we have seen that, say, shock angle, for example, when we consider a compression corner, the angle, wave angle beta, we have always calculated based on the oblique shock theory. Oblique shock theory, the theoretical formulation, does not account for viscosity. But despite that, even experimental studies and numerical studies, CFD analysis, which incorporates viscosity, give results which are very close to inviscid flow results, which means that shock wave angle, particularly when you have attached shocks, the wave angle beta is it is safe to consider it as a parameter which is not strongly affected by viscosity. Similarly, the wall pressure distribution. Pressure distribution, to a great extent, actually, pressure distribution can be dependent in certain situations, but there are instances where the wall pressure distribution can also be considered to be independent of viscosity. So even in a viscous flow, you can get meaningful results, or at least estimates of pressure distribution when you disregard the viscosity. And then wave drag. Wave drag, as we know, actually the definition of wave drag itself is uh, in order to decouple the drag forces from the frictional ones. So wave drags are purely because of the pressure gradients that are caused by shocks and expansion fans. Shocks and expansion fans, where we disregard the viscosity when we do the calculations, and we still get reasonably good results. So wave drag per se can be considered uh, to be somewhat rather actually wave drag can be considered to be independent of viscosity. So there are instances where we can have shock angle, pressure distribution, wave drag, etc., which can be calculated safely without compromising a lot on the accuracy. We can estimate these values. But there are other key parameters which are solely dependent on viscosity, or primarily dependent on viscosity: skin friction drag and heat transfer. Friction drag is a term that you are familiar from fluid mechanics. The drag that is experienced at the wall because of the viscosity, that is because of the intermolecular force, and the fact that the fluid, whenever there is a velocity gradient within the fluid, there is a force that resists it. So that which is in the opposite direction, and that results in the viscous force. And we have coefficient of viscosity, which sort of quantifies that particular property of the fluid. And the drag caused by this viscosity is what we refer to as the viscous drag, or the skin friction drag, or just friction drag. Similarly, heat transfer. Now, heat transfer, say when you have heat transfer between the fluid and the solid surface. Remember, in hypersonic applications, as we have discussed several times earlier, the temperatures can go quite high, and that's because wherever there is a velocity gradient, the conversion of velocity to internal energy can be significant, and the internal energy itself manifests as temperature. And in the presence of heat transfer, a significant portion of that thermal energy will be transferred to the solid. So you have transfer of heat between the solid and the fluid. And when you have that kind of a heat transfer through the solid or even at the interface, properties like conductivity become very important. So thermal conductivity, say here the thermal conductivity of the fluid. In fact, thermal conductivity and viscosity are sort of analogous. One relates to heat transfer and the other relates to momentum transfer. Thermal conductivity relates to heat transfer, and viscosity relates to momentum transfer. And by similar means, by molecular diffusion, or the effect of molecular layers, if you consider it as several layers, the heat transfer because of molecular contact is referred to as conduction. And similarly, the momentum transfer because of molecular interaction is referred to as viscosity, or rather, which is responsible for the viscosity. So these two are related. And so what I'm trying to say here is that when you have heat transfer, the effect of conductivity and hence viscosity are important. Okay, so these are phenomena which are important from the real for the real applications of hypersonic flows. Now let's look at some of the instances where they are applicable, where they become important. The re-entry trajectories we have discussed earlier also. So the ballistic re-entry, like that of Apollo. This one example where you have a large velocity at the time of entering, and this is not just while re-entering the atmosphere from the orbit, but even even when you are relying on an earthing propulsion system to propel the mass or propel the payload to the orbit. I repeat this: when you use an air-breathing propulsion system as opposed to a rocket, which is more commonly used. So if you are using an air-breathing system to propel, say, a satellite to a near-Earth orbit, even in that case, the velocities that that will result at higher altitudes will be very high. Now, when you have such high velocities, the friction drag becomes prominently high. Now let's look at the velocity altitude map that is shown there. Here you can see the constant lines, which are sort of lines of Reynolds number, constant Reynolds number. But otherwise, if you can, I'll just try to show the. Let's consider any of these. Okay. What does it show? It indicates at a given altitude what is going to be the velocity. Basically, that's what is meant by the altitude velocity map. Now, this velocity, remember, it is in kilometers per second. Kilometers per second, so very high values. So say for example, say 7 kilometers, 8 kilometers per second is quite high value. So and then how does the velocity vary with altitude for say a typical re-entry vehicles is what is shown by the different graphs. And on that are superimposed lines of constant value of rho v by mu. Rho v by mu. D is is considered to be per unit length. So this is a convenient way to decouple the dimension from the definition of Reynolds number. So sometimes they call it as unit Reynolds number or Reynolds number per unit length, etc. Anyway, so these are shown for some levels of Reynolds number, which indicates that. Now let's see what's the implication of this. Say at very high altitudes, like say 100 kilometers or maybe 80, 85 kind of levels of altitude, you can see that the Reynolds number tends to be quite low. So you can see that, say here it is 10⁻⁶, 10⁻⁵, 10⁻⁴, 3, etc. So this is in the decreasing order of Reynolds number, primarily because density drops, rho v d by mu. So what it means is that at higher altitudes, altitudes of flight, the velocity will be high, Reynolds number will be low, and of course, velocity is high means the Mach number is high. At the same time, Reynolds number can be low. What do you mean by low Reynolds number? Rho v by mu. Here, if you disregard d for a moment, rho v by mu is low, which means that the relative effect of viscosity is high. We know that Reynolds number is referred to as or quantified as the ratio of inertial forces to viscous forces. So low Reynolds number means, practically laminar region means the region where viscosity dominates over inertial forces, which means that the resultant force is dominated by viscosity, or rather the resultant phenomena around the body is dominated by the effects of viscosity. So and the velocity, as we see, is going to be very high. So this is the range that we are interested in hypersonic aerodynamics. So in the real applications of hypersonic aerodynamics, like re-entry trajectories, the viscous effects can be very high. And that's just re-emphasizing the same concept that we just discussed here again on velocity altitude map. So this say for like space shuttle kind of trajectory, you can see that as it comes down, as the various points are marked on the table, it passes through different velocities, but at higher altitudes the velocity is high, and as we have just seen, the Reynolds number is low. So whether it's a shuttle, the space shuttle kind of configuration, or a ballistic re-entry, in all cases, the combination of high Mach number and low Reynolds number are important at higher altitudes. And that is where we require, so which means that the viscous interaction has to be accounted for both the consideration of from the perspective of momentum, that is from the perspective of friction drag, as well as from the perspective of heat transfer. Heat transfer, we'll be actually discussing more about heat transfer, but just be reminded that heat transfer is important because you have higher thermal energies and you will have higher thermal energy gradients, which will have sufficient, which will have a very high amount of energy being transferred from the air around onto the shield or the body of the flying object. Okay, now how do we include the viscous effects? As we always know, there is no closed form solution which is possible when you consider viscosity. Navier-Stokes equations, full Navier-Stokes equations, as we know, are the are a set of strongly coupled nonlinear partial differential equations. So as of now, there are no closed form solutions or methods that can lead to closed form solutions. But at the same time, we need to start the analysis from Navier-Stokes equations as opposed to Euler's equation. So far we have been focusing our attention whenever we needed any reference to the governing equations, we relied on Euler's equation. That's because the viscous terms were to be neglected. We were neglecting the viscous terms. But the moment we say we are going to consider viscosity, we need to start from the Navier-Stokes equations. Now, starting from Navier-Stokes equations, how can we even hope to have a solution? The first step is the boundary layer approach, and which is what, as you know, as identified by Prandtl, which is considered to be one of the most important or most intellectual advancements in 20th century in fluid mechanics. The Prandtl's observation basically is that the viscous forces can be considered to be dominant over a very thin layer, and the rest of the flow can be considered to be inviscid. And that this brought in a lot of simplification in the analysis of flow field around bodies, because outside this thin layer, you could assume the flow to be invisible without sacrificing a lot of physical accuracy in the prediction. So that's basically what we call as boundary layer, the thin layer adjacent to the surface, solid surface, where the viscous forces are prominent. So the equations can be simplified in such a way that except regions which are very close to the surface, the viscous terms can disappear. So by doing so, you are accounting for viscosity. At the same time, you are relying or you are making use of the convenience of Euler's equations outside the thin layer which is close to the surface. And then, so that will lead to what is referred to as the formulation of boundary layer equations. So starting from full Navier-Stokes equations and then making use of the boundary layer concept, you can formulate the boundary layer equations. Now, can we solve boundary layer equations as such? They still, I mean, even then will be restricted, but since particularly because we are talking about compressible flow, but then we can have similarity solutions for boundary layer equations, which is what is made use of in the analysis of viscous flows. So on the theoretical branch, actually we are discussing along the theoretical branch, or rather analytical branch. The analytical branch, this is the only route that we can do to go about by for incorporating the viscous effects. The other parallel branch, of course, is CFD, computational fluid dynamics, where you can, which is obviously, as you know, is a numerical method. You discretize the domain, discretize the equations, convert them to a set of partial differential equations, algebraic equations, and then solve by an iterative process. So that is CFD, and that approach can incorporate viscosity without any issue. So so if you are not, if you don't have to go for an analytical solution, or if you have the resources and time to go for CFD, then you can take that path where a solution can be obtained by incorporating viscosity. What we are going to look at here in this series is how to model the viscosity through the formulation of boundary layer equations and the similarity variables associated with that. So we'll since we are first talking about the Navier-Stokes equations, we'll just start the discussion with Navier-Stokes equations, particularly because we have been so far talking about Euler's equations. Navier and Stokes, two independent researchers, and if I understand correctly, they had independently formulated these equations, and that's why the term is given as, and probably they worked almost on the same time, but in two different parts of the, or rather independently. So, but then got the same kind of formulation for the the variables that they were working on. So that's why the equations, the group of them are known as Navier-Stokes equations, and the continuity, momentum, and energy equations. In fact, a difference in the nomenclature. In fluid mechanics, when you say Navier-Stokes equations, usually they refer to only momentum equation. So when you say in the terminology of fluid mechanics, when you say Navier-Stokes equations, that it means only momentum equation. This may be probably because historically, as I mentioned, these two people worked independently, and probably what they formulated was the momentum equations mainly, and that's why they are referred to as momentum Navier-Stokes equations. But in CFD, when you say Navier-Stokes equations, it just means the governing equations where viscosity is incorporated, which means that it contains or refers to both continuity, momentum, and energy equations by incorporating viscosity. So the governing all the three governing equations with viscosity are referred to as Navier-Stokes equations in CFD, whereas in fluid mechanics, only the momentum equations which is related to, which is incorporating viscosity, is referred to as Navier-Stokes equations. Okay, so now we'll look at the forms of the equations. So any questions so far about whatever is mentioned till now? Okay, we move forward then. The continuity equation. Again, continuity equation is probably the most commonly used one, and probably the most simplest and the familiar one, which says dou rho by dou t plus del dot rho equals 0. Rho is inside the bracket because we are talking about compressible flows. Otherwise, it could be rho del dot p. And dou rho by dou t, the first partial d rho by dou t is retained because we are considering transient phenomena as well. So the full form of continuity equation, dou rho by dou t plus del dot rho v, the divergence of rho v, right? That is equal to 0 is the most compact representation of continuity equation. And as we know, there is no role for viscosity in the formulation of continuity, because continuity refers to mass, conservation of mass, right? Mass, in the formulation of mass, in the consideration of mass, the viscosity is not a parameter, right? Viscosity, which is more related to momentum and the transfer of energy, viscosity is not related to mass. So that's the reason why in continuity equation, viscosity does not show up. Not only that, it remains the same whether we are considering Euler analysis or Navier-Stokes analysis. The continuity equation is not affected by the viscosity. But now let's think of momentum and energy equation. In momentum equation, certainly velocity will have, viscosity will have to be encountered, because we are talking about the momentum equation talks about the rate of change of momentum and the forces acting. So when we talk about the forces acting, and we know that there can be body forces, and if you neglect body forces, there are still surface forces, and the surface forces are constituted by pressure forces and viscosity forces. So as long as you are considering all the forces, all the surface forces, you will have to incorporate, you will have to consider momentum, viscosity in the momentum equation. Similarly, in energy equation basically is a rate, related to the rate of energy or a transfer of work, etc., specific work, etc. And so when we consider work, what do we mean by work? Work done by the forces. So what are the forces? Again, the pressure forces and viscous forces. So if you are completely formulating the energy balance, then you need to incorporate the work done, or the work done by the viscous forces as well, which will have obviously the viscosity term coming in that. So continuity equation is not impacted by viscosity, but momentum and energy equations will be having viscosity components in that. We'll take a look at the momentum equations. You would have seen them in your fluid mechanics and probably also in the CFD course. Momentum equations. The way that we state them are similar to Euler equations, except for that there are the viscosity terms are present, or the terms that come because of viscosity are present here. They show up as viscous forces, or rather in terms of shear stresses. I'll try to. So rho du by dt. Now rho is familiar. Du by dt. This is what you call this du by dt. This capital Du and capital Du by dt. What's a term that you are familiar with from mathematics?
Substantial derivative.
Yeah, substantial derivative. Exactly. Some people call it as material derivative. So everybody has their own reasons to call it the way that they do. But then it's a way that the temporal variations, that is the time variations, as well as spatial variations are merged together, or rather bridged together. So the substantial derivative or the material derivative rho of u with respect to time, rho du by dt, can be expressed as, now what remains in the equation are the terms that become because of the forces. Minus dou p by dou x because of pressure forces, and the three terms that come are because of shear forces. Shear forces which come because of viscosity. Tau xx by tau xx, tau yx, tau zx. Now this xx, yx, zx, they are coming because of the consideration of the cross forces in the respective directions. I'll just try to this is you would have seen this. I'm just trying to refresh that how the elemental how a fluid element is considered, and from where the energy balance as well as the force balance come from. So when you consider the forces, say for example, I'll just show one so that we can infer the rest similar to that. So if you consider this phase, that is FGCB, the phase away from origin, which is facing the x-axis. Okay, that is the phase which is in the the YZ plane, YZ plane. Okay, if you consider the forces acting on it, the pressure forces are obvious. P, that is a static pressure. P plus dou p by dou x into dx. Why dou p by dou x into dx? Because we are considering the pressure to be P at x equals 0. So away from that, there is a pressure gradient which is accounted in the x direction as dou p by dou x, and that gradient multiplied by dx, dou p by dou x into dx. So that's the pressure, and that multiplied by the area of that phase is dy dz, because it's in the YZ plane. So this is the pressure force acting in this plane, the pressure force. We'll just call it as pressure force, PF. Whereas the shear force acting on this plane is, say, you have tau xx, that is the shear acting on this plane along the x direction, that is acting on an area which is normal to the x-axis and along the force being along the x direction, that is tau xx. So again, the same way as we take the gradient, on the other face you have considered it as tau xx into dy dz. So here the corresponding shear stress will be tau xx plus dou tau xx divided by dou x into dx. That's the shear stress that multiplied by the area dy dz. So that accounts for the shear coming on that phase acting along the x direction. Similarly, on the other directions also. Now, here we have tau xx. So, for example, in the top plane, on this surface, you will have tau yx because of that particular plane, and tau yx divided by dou y into dy dxz. Because we are considering the shear force acting on this plane, which is on the on this face, which is on the y sorry, which is on the zx plane, and we are considering the force that is in a plane which is normal to the y-axis. The force in a plane that is normal to the y-axis acting along the x direction is what we have as the tau yx plus dou tau yx divided by dou y into dy plus dx dz. So by this way, actually all forces are not shown on this, but if you account for all the forces on acting on the various phases of the fluid element in this way, then we can eventually get the momentum equation, and that's how all these are formulated. So what we have here is x momentum, y momentum, and z momentum equations. And usually it's a practice to group the shear stress terms together, and that's how it is shown on the right hand side. Tau xy, tau xy is equal to tau yx is equal to mu into dou v by dou x plus dou u by dou y. Now, there is an assumption involved when you write it like this. Tau xy is equal to tau yx, which means that the shear stress is sort of independent of direction. So you are assuming isotropy of the shear stress. Because if you don't do that, actually, you may have, say, like non-Newtonian fluids, etc., where such assumptions are not valid. There it becomes more complex, and you cannot formulate it this way. So we are now restricting the attention to cases which are quite common, where you can assume tau xy is equal to tau yx. So when you do that approximation, then the shear stress terms can be put together, and that's where the coefficient of dynamic viscosity can be introduced as mu into dou v by dou x plus dou u by dou y. Remember, dou v by dou x, a velocity gradient term. Similarly, dou u by dou y, another velocity gradient term. So these are velocity gradients. And as we know from the fundamental formulation of Newton's law of viscosity, the viscous force is represented as a result of the, or comes because of the velocity gradient. So that is the shear stress. You consider it as say tau is proportional to the velocity gradient, and that's where we introduce the coefficient of viscosity as a constant of proportionality. So mu multiplied by the sum of the velocity gradients, and similarly in other directions also, tau yz, tau zx, etc., etc. So this is how the momentum equations are formulated by considering the various stresses. Now, I'm sorry. Or I'll just leave them, because I'll make use of that anyway to explain this. The energy equations. Energy equations on say you have all the terms on the right hand side, which represents the transfer of energy because of various forces, and the energy transfer because of heat transfer. Now let's look at the left hand term first. Again, you have the substantial derivative. You have the substantial derivative of E plus V squared by 2. E, the internal energy, V squared by 2, the kinetic energy term, the specific kinetic, both are specific. So the net energy term on the right hand side. Now, this energy, actually the whole thing comes, the formulation comes from the perspective of the first law of thermodynamics, where we relate the rate of change of energy to the sum of heat and work transfer, Q and W. Remember that. Q, the heat transfer, W, the work transfer. Work transfer is by different forces. Q is by heat transfer, which is because of temperature gradient. Okay. So when you look at that, if you are able to recall that formulation, then we should be able to recollect or connect these terms appropriately. The first part refers to heat transfer, or because of the thermal gradients. Okay. Remember, we are looking from the perspective of energy Q. I'll write as minus W. Q, rate of heat transfer minus work transfer, etc. So now, if you the first is related to Q, that is thermal energy transfer. Now, what are the forms thermal energy can be transferred? One way is volumetric heat transfer. That is, within the control volume, if you have any, say, chemical reaction happening, if you have combustion happening, then kinetic thermal energy gets converted to heat. So you can have a volumetric heat release. It could be maybe also by radiated from outside, but it applies across the volume. So if it is per unit volume if it is Q dot, then rho into Q dot can be considered to be the energy that is transferred per volume. So this term, the first term, is to account for any volumetric heat release or volumetric heat transfer. The remaining terms which have temperature gradient, they indicate transfer of energy from outside. Transfer of energy through the wall, say, assuming that is not an adiabatic wall, that is, if you have heat transfer through the wall, the conduction through the wall can have energy, can have thermal energy coming in. Now, conduction, as we know, is modeled by the Fourier's equation, right? Dou T by dou X. The famous formulation for conduction, the Fourier's equation, Q equals minus K into dt by dx. Q, heat transfer due to conduction, is equal to minus K into dt by dx. Minus K because it's going to be in the opposite direction of the gradient. K into dt by dx. K is the conductivity, okay, thermal conductivity. So the K dt by dx is the Fourier's term, K dt by dx. Now we are considering a three-dimensional domain, so it could be dou by dou x, dou by dou by dou by dou z, depending on which gradient, which direction you are looking at. So K into dou t by dou x, dou t by dou y, K into dou t by dou y, dou z, etc. account for the thermal energy that is being added. So volumetric heat transfer and heat transfer from outside, those two are accounted by the first series of terms. So, so that is, they all account for what we have marked here as W. Q. Now, what remains W? W is nothing but the work done by external forces. What are the forces? Pressure forces and the pressure forces and surface forces. Actually, in this formulation, we are not considering body forces. Otherwise, say like gravity, etc., which are neglected. So otherwise, we should have a term for gravity also in this. That's neglected anyway. So you have pressure forces with the term with P, and then surface forces, and then viscous forces, which we have, as we have just seen, the various shear stresses which come because of viscosity. So all these terms come because of the work done by the shear stresses. All of these. Okay. So in summary, what we are seeing here is a fluid dynamics statement of the first law of thermodynamics. First law of thermodynamics stated in terms of fluid dynamic properties for an unsteady viscous flow with heat transfer. unsteady viscous flow with heat transfer. Okay, with volumetric heat transfer as well as heat transfer across the surface. Okay, so this is the general form of Navier-Stokes energy equation for viscous flow. Okay, now so we have the equations, but then solution, as you just mentioned, the two approaches are, one is boundary layer formulation and the other is a CFD. CFD can tackle these equations without further simplification. CFD relies on discretization, but not so much on simplification. So CFD solves the Navier-Stokes equations without further simplifying them, but uses a discretization. So any accuracy error, etc., are involved, creep in only through the discretization in CFD. Okay. Now we of course our focus, as I mentioned, is going to be based on the boundary layer formulation, and we will see how we normalize these equations and then define the similarity parameters that can be applicable for viscous flows. I think I will stop here. If you have any questions or anything to be clarified from what I have mentioned so far, I'll try to do that. Okay. Now, how about the assignment? I could not locate any group submitting the assignment except for group 4, which has sent to me directly. What's the status of others? Others have submitted, uploaded, sent, or I could not locate it actually. Can you please respond on this? Team 1.
Yes, sir. We have the assignment ready, sir. We haven't submitted.
You can please upload it on this one. Okay, so that
Yes.
in the next few classes, we may dedicate some part of the class, this one to for your presentation. Presentation doesn't take much time, I know. It's just 2-3 minutes, but I would like that to be done. So team 1 has. How about team 2? The group 2.
Yes, sir. The presentation is ready. We've not yet submitted it, sir.
Please do that. Okay.
Yes,
Whatever
sir.
you have, just upload it.
Yes, sir.
Same with 3. 3 is also ready.
Yes, sir. The same with us also.
Yeah, please do that. I mean, all of you do that today, so that even tomorrow we may be able to spend some time to do this one. 4 has sent it to me already. I think I would request you also to upload it. Let it be all on one place. So for me
Okay,
also
sir.
it'll be easy to
Okay.
yeah. So you please upload it on this one. For how many groups we have? By the way, 5, right? 22. How many groups we have? 4 or 5? 5. So what group 5 also? I hope you are ready with the presentation, right?
Yes, sir.
Yeah. So please upload it so that we can finish that. Okay. Anything else? If no other questions, we'll continue in the next class. Okay, apparently not. Okay, then we'll see in the next class. Thank you and bye to all of you. Bye.
Thank you, sir.
Thank you.
Thank you, sir.